to let you know that we have another exciting meetup on Friday at 3 p.m. at USC's Information Science Institute, and you should check that out. I also wanted to note that even though you guys did register video on, but we also have a sign-up sheet for each of our meetups. So I did share the link to our sign-up sheet for tonight on the Facebook page and the Meetup page, and I would appreciate if you guys go in and enter your information. So if you're looking for collaborators, you want to network, or you want to get hired, or you want to recruit like talent, and just like get to know people, I think it's best that you guys go on that sign-up sheet and add your name. We have one for the last meetup, and we're going to just be adding the names to our database. So this is Deb. He's one of my dear friends, and he's very good at what he does, and he's going to tell you about his work at video.
Thank you. So, how many of you are probably wondering what on earth deep learning is? Just to get a throw in. Yeah? So, everyone else is an expert? Space in between. So how many are experts in deep learning? Okay. Alright, well, you guys might be a little disappointed if you're an expert here, because I'll try to cater this more towards a background in deep learning, what it's all about. Have a little demo or a do-it-yourself exercise, so hopefully at the end of this you can go home and try it out. So Jack over here, he runs our company blog, so he will have a write-up about this, so you can go home, test it out, play with it yourself. And then I'll talk about a couple of applications in Adtech. Can't really go too much into the implementation details there because these are our products and future products. And then at the end, there was some interest here about having a hackathon, some sort of visualization and deep learning hackathon. So how many of you might be interested in that? Okay. So ideally we'd do that on a Saturday. We can provide the space and also some of the resources, the cluster and everything to run it. And for that, Michael Ullman at the back in orange, and then Sophia. After I go through my talk, they can talk a little bit more in technical detail about some of the tools that we use, including Spark and Jupyter and SparkNet that you might find useful in the hackathon. So we can help you run, spin up some clusters, run whatever you need. So, going a bit into the history of deep learning, why did it all come about? So, it all starts with a data set that you can fit with linear regression, right? Straightforward, simple. Don't even try deep learning. When your data gets more complicated, something on the right-hand side, that's when you need something more complicated, a quadratic function, for example, right? So when data is more nonlinear, it can be fit just by linear regression or simple regression alone. That's where deep learning starts becoming handy, because you can encode nonlinear functions. So the first step of this came about with Marvin Minsky coined the term perceptrons. So what perceptrons do is they encode a kind of linear regression part here. So each of these x0, x1, x2, xn, there are different dimensions of the data set and a weight assigned to each of them, and there's a simple sum, so this is the linear regression pattern. But this is passed through a nonlinear function, so here it's sigmoid. So what that allows you to do is, in this example, use it for classification, but encode more nonlinear functions with it. So take linear regression, pass it through a nonlinear function to get much more interesting functions out of that. Why it got a lot of interest in the neuroscience community is is Rosenblatt thought of this as perceptrons could model neural synapses. So in the brain, what you'd have is, how many of you are familiar with a picture of a dendrite? So in a typical dendrite, you have a cell body, an axon, and a lot of inputs coming to that. So one way of thinking about it, why perceptrons were very interesting for neuroscientists, were all the inputs coming in were from different cells. And there's a cell body inside, and it fired once it reached a certain activation energy. And then you got an output through the axon. So that became an interesting model for a very simplistic model of the brain. John Hopfield at Caltech took it a step further, and where now all of these inputs could come in to a densely connected matrix, and that was actually a pretty realistic model for memory in the human brain. So that got a lot of interest in among computational neuroscientists. So that was fine, but the question was, once you start fitting a nonlinear function like this, fitting this is very difficult. With regression, there's a very simple closed form solution, and you get these weights out, super simple. But how do you handle something like this nonlinearity, right? Especially now that you're dealing with a multi-layered neural network. So these perceptrons feed into other perceptrons, which feed into other perceptrons. So training all of that together and finding the weights for these things are very difficult. So the work stalled for a while until Jeff Hinton and Rumelhart came up with the backpropagation algorithm. So what the backpropagation algorithm does is, so you have a large training set, and you have a multi-layered neural network with input layers, hidden layers, output layers. It goes through a forward phase where the training data is passed through, and it identifies some label there. And it does a backward step as well, where each layer tries to recreate the layer before it. So it's training on its own. So a version of this is a recurrent neural network, which is used for unsupervised learning, where the output layer just has connections to itself and to other layers below it. So there's a process where you pass the data forward and you see what you get, then run it backward and get an error out of it. And the goal is to minimize this error over multiple iterative steps. So another advantage of neural network, especially a multi-layered neural network or deep network, is that it's a generative model as well. So you can run it in forward motion and generate things out of the network. Try to figure out what the network has learned. So there was an interesting article by Jeff Hinton in Science magazine in 1995, where he conjectured that this is another way of, people were thinking about the brain as a neural network. So the conjecture was that this is, going forward is the waking phase that we all have, and it passes through and our synapses get trained. And the dreaming state is when the neural network starts generating on its own and to calibrate against what's going on. So that was a postulate of why we wake, why we sleep, and why we require sleep to train our brains. And most animals that have complicated brains actually dream. So after backpropagation came into being, then it was a race to sort of build more and more complicated networks for more and more complicated tasks. So the key breakthrough was in 2006 with Jeffrey Hinton again and Raslan Salakutnikov, where they trained a very large restricted Boltzmann machine, convolutional neural net on a large data set. This algorithm to do that really opened the floodgates to more and more complicated and deeper neural nets that came to be called deep nets. or deep learning. This paper kind of coined it. And then it got more and more popular as industry took off. So Demis Hassabis started the company DeepMind, which got acquired by Google. Then Jan LeCun went to Facebook. Jürgen Schmidhuber, who worked in the current neural nets, a number of startups. Li Deng went to Microsoft. Ilya Sutskever, who was a student of Hinton, started a company called OpenAI, which was partially funded by Elon Musk to explore beneficial applications of deep learning and AI. And I think this whole field became very mainstream and popular once these type of books started coming out, like Deep Learning for Business Leaders. So, just my personal background, I worked with Jeff Hinton. So this history is, by the way, very biased because of my background too. I worked with Jeff Hinton and his group in Toronto, then worked with Demis Hassabis, and also at the Computational and Neural Systems group at Caltech. And I've been utilizing deep learning in my past 2 startups. So the question is, what is deep learning really good for? I mean, you can obviously massage it and torture it to work in a number of settings, but where it really shines is for natural scene statistics. So when you have images, speech, or when there's a lot of latent structure that you don't necessarily want to program in. So you might have seen examples of deep learning algorithms playing Go, right? That is where it learned the underlying structure of the game, underlying representations of the game, and you didn't have to hard code it through repeated play, lots and lots and lots of examples, right? And images, speech contain dense data, so it's really good for training a neural network. So there are lots and lots of pixels within an image, so that's good fodder for a deep learning network. What it's not good for is where there's a strong reason to encode knowledge, like for example, for semantic knowledge representation. So first order logic, any kind of planning, scheduling algorithms. No point running deep learning to figure out airline schedules. Pointless to do that, right? There are other tools for that. Or for specifying priors, or any type of Bayesian inference. Again, where you have to encode a particular set of priors, deep learning isn't really the best tool, although you can use it for that. So, just to give you a kind of a teaser into how this works, and I really encourage going to this site yourself and checking out what it's all about. So, this one, the TensorFlow has a playground which allows you to play with this. I'm going to pick a very difficult data set to work with. So this one, again, you have to learn, in order for you to classify, so the yellow and blue are different classes, okay, and your boundary that can separate this has to be highly nonlinear, because it has to go through and separate it here. A line just won't do because you get 50% error rate. So you have to find one that kind of cuts through all of this, right? And the TensorFlow playground allows you to specify different activation layers. So the most basic one is linear. Linear doesn't do anything for deep networks. I mean, you lose the whole point of it. So if you try running it with just linear input, so here is the linear set of inputs here, you can add these, right, and run it. For each of these, you can see the different boundaries that it's learned. So here, it's obviously not doing each of these hidden networks are not doing a very good job at separating these two classes. So this one has learned, it's classifying everything here as the yellow class, so it gets all these wrong. And so are all these. So when you look at the output layer, again, the second layer of it, it's not right. learning the right combinations. So you get a really high error rate. So your test loss here is 46%. So how can we do better? It's by trying a tanh loss function. So you get interesting boundaries like that. Maybe there is hope there, right? And the output layer looks like this. So now the error rate immediately goes below what we had before. Because learning much more complicated boundaries. But this is a very difficult data set to separate, and it kind of tells you that unless, really the only way to separate this is unless you go and map this to a higher dimensional space, it's really hard to separate this on its own, even with multiple layers. But it still did significantly better at 0.3. So I recommend trying this, playing around with it. So I thought for everyone here, it may not be very interesting for those who have already played around with TensorFlow. Jack's going to have these set of instructions for how to run and train your own images at home on your laptop. So it's very simple because there's a Docker image for this already. Docker is just it's a container, so you can run it with the same configuration on any machine. Make sure when you download and install Docker, get this Docker image. Make sure you optimize VirtualBox because on its own it's going to have very little memory, and at least set it to 8 gigs of memory and 4 cores. Then you can use your own training set. There's one that's freely available. It's got a bunch of flowers in it. And make sure you update your code, the latest one. Then the first step is to build the TensorFlow code, because TensorFlow, by the way, is an open source code from Google. It's written in C++. We don't particularly find it useful here because TensorFlow hides away a lot of details. So when we deal with images, we can't get the feature vectors, for example. So that's not particularly useful for us. But it's a good way of getting used to learning this. And then the next step is to train the model. So I started it, and I thought it would finish, but it's still running. So the training phase is still running for the last half an hour on my laptop. So just beware. If you're trying it at home, it will take you, with 4,700 images and training all of that, it will take you at least a few hours to run all the way through. And your laptop will definitely heat up. So the training phase is super simple. So you choose the set of training images. So the ones that we have downloaded, the great thing about it is it comes with its own set of labeled images as well as there's a bunch of flowers and what type of flowers there are. There are different specifications. I think it's best to just look at our blog after this and try it at home. Also, testing the classifier is very simple. You can give it a set of images and see what the resulting outcome is. What it's really doing in the background is in the training phase, it's really learning a set of embeddings. So if you look at a bunch of images all on their own, and the pixels alone, it's really hard. If you embed it in Euclidean space, just by looking at pixels alone, it's really hard to decipher what object is what. Right? So what it's doing is, at the essence of it, deep learning learns a manifold of classes. So it's learning in a very high dimensional space. Here's a cartoon which shows you how it separates. The classes get separated on this underlying representation. So you can get your set of training images. After training it in this higher dimensional space, the classes will separate out. So once you give it a new test image, from an unknown set, it learns to map it to the closest image that it knows. So if your training images only consists of dogs, cats, and dogs, horses, and automobiles, if you give it a cat image, it will try to find something that's close to it. So if you try this at home, I'll invite you, we can't go into this because this is kind of much more involved, but I really encourage you to try out the Deep Dream TensorFlow. So you can take your any trained network and run it in reverse and see the type of images that it generates. So example of running this on, so I took ImageNet and you run ImageNet and get a whole bunch of different classifications. If you run Deep Dream on it, you can start seeing very interesting things, right? So if you feed it an image, right, and you ask one of the, not the output layer, which classifies everything, but the layer before it, try and reconstruct the image that it sees. You start seeing very interesting, it tries to reconstruct it with the objects that are trained in that layer. So here, just like fish images show up. So these are interesting hallucinations that come up to try to recreate things within the neural network. Or here, it's like a bunch of flowers. So it's trying to create this scene over here with a bunch of flowers. Same thing with this tree here, and I don't know, try to create it with some other set of objects within ImageNet. Here it's trying to recreate that with a set of cats. So you get all sorts of interesting things when deep networks start hallucinating. So that's why it's called deep dream, kind of like some of our dreams. So I want to show you something interesting, which is Jürgen Smedhuber's group tried it with videos. And he trained a network on a bunch of TED Talk videos, right? And tried to generate it and see what would happen. Sorry, that's an ad. We can't skip ads here.
Spies. The new season premieres tonight at 10. Only on EMC.
Ideas worth generating. RNN stands for recurrent neural networks.
We have to have more self-compassion to experiences the power. In fact, we really believe in the supercomputers, where they make them to think about a standard security. It's a physical thing about data in the human beings, but in the United States, the interesting stuff that we think would be a lot science ones. But in the computer, the great country cannot be complicated. It means that when we look at the might of machines, we should also think climate change to convince the brain about projects from the Solar Social Society. Years later, we want to end up with mathematics running the show The Democracy. But the government will have the policy big governance in the case of the question of human beings. So here we end for democracy. Science was to say that moving to the context, and then our commitment that has been the past the world. This is a computer
There's also a Twitch channel where you can put in a topic and it starts generating different hallucinations or images. So you can add that to the same.
Or to be able to solve the data in
Alright.
an astronomical spike.
Something. So the words he's saying, he can only use words that are on that manifold, right?
Yeah.
Yeah. Okay.
So it's running in reverse. So what they did is they took all the TED Talks labeled technology, transcribed them, learned the words from it. It has a sentence generator, so it can actually create at least meaningful sentences, not semantically meaningful. But
You could do something funny like take all the Donald Trump speeches and generate fun reviews.
yeah, who knows how that might sound.
Well, there's a Twitter bot that they actually did. There's a postdoc at MIT and he did that. So he trained on Donald Trump's Twitter account and
Deep Drum.
Deep Drum.
Oh, okay. And no difference?
And you can't tell the difference.
So, yeah, there's a lot of other interesting examples of people creating neural network art, combining like impressionist art with Picasso and seeing the results. So let's go back to Adtech and some of the applications where we use deep learning here. So what we do, there are three major components. We use at video ad, we do real-time bidding. That means we are bidding on every single ad impression. So that occurs billions of times a day, right? Each ad behind the scenes, what happens is whenever you open a website and there's an ad opportunity, it goes into a real-time bidding auction, and all the participants get less than 20 milliseconds to submit a bid in the auction. This happens billions of times every day, which is why we have to, the first thing we have to do is create a very fast, efficient data platform on Apache Spark. And if you after this talk, Michael will talk a little bit more about that. The other thing we do is for every impression, we get a user ID. Again, this is hashed, so we don't know the individual, but we have an ID associated with them. And we take these user IDs and cluster them to form a video app ID across all screens. So across TV, mobile, desktop. And then from that, we can create a consumer graph to find lookalike users. So one place that, it's probably the most important part of ad tech, or at least video advertising, but it's the least quantitative, is the creatives, the ads themselves. I mean, that part is still relegated to the madmen, and we're just crunching data here on real-time bidding and device graphs. Tons of data is available. And the reason for that is for creatives, there's not a lot of data available that can at least be parsed by machines, right? There's what makes a good creative, maybe with some scotch and everything, you can generate a good creative. But the purpose here is, can we do something similar? Can we generate tons of data from these ad creatives and then throw them into, at least try and create some Schmidt, like that TED Talk like creative. That would be the goal, right? And maybe someday it just runs on its own and it's even better than what you have out there. That's the dream. So the first, why are we interested in deep learning in ad tech? There's lots of image and video data for video advertising. It's a lot of high dimensional data. So each available impression that comes in has over 100 different fields in it. It's a very high dimensional data set. And then most of them don't have labels, so we want to learn some sort of latent representation in that data. So, one place to use this is in video content classification. So we're going to categorize video creatives. We're going to categorize video creatives into different classes. So this could be used in making sure that the right ad is shown on the right page or on the right content. Also, other simple things like, are the creatives brand safe? There are different criteria. You can look at the video and classify that as not suitable for kids, etc. But the deeper question is, what are the factors that drive high-performing video creatives? That means by high performance, we mean more and more people are likely to watch it, click through, see it all through the end, high viewability, which is one of the key metrics that drive the industry. To a human, it'd be the obvious, why does this ad suck? Whereas this one, the Carl's Jr. ad, has one of the highest viewability ratings ever, right? So can we figure out more machine-generated data to do these type of inferences on our own without the need for a human? So for video content classification, what we do is take an image. This is one of our ads.
CEOs are all born with
And
the same abilities, but they
For
do share
each of
some
these,
common traits.
for a video, we'll break it down into frames.
Tenacity,
So we can
and
use
enduring
something like
spirit are
FS
just a few.
and spec to break it down.
CEOs and business owners are born
And then, for each frame, identify the objects, the recognized faces, and text in it. Again, very simply with the image, something like ImageNet that we use to train this on.
CEOs are all born with the same ability.
Yeah. So I chose this example because it kind of shows you some of the limitations of this approach to date. And it all depends on the training set. So this one, it classified it as play with some score, a vehicle, and a toy. It's kind of confusing between the two. This one identified as a toddler and a gadget. It thinks this is a vehicle. Partly because in our training set, I don't think we had examples of this. If this becomes important, we've got a rich training set. We can classify it as, I don't know, what is it?
Wagon.
Huh?
Toy wagon.
Toy wagon. Okay. All right. So now we can add that to a training set. But this is classified as a beverage and drink, partly because we don't have those training data, trained person. So this identifies as a human action. At least it identifies this as a balloon, some sort of racing, cycle sport. So this is a funny example of this because this video is kind of wacky. But what we can do now is run all the video that we can, get our hands on and run it through this classification algorithm and see what are the elements in a video that drive higher performance. So how can we do that is in our console, in VideoAmp's console, we can look at the data set, like we can look at the video, the history of playing it, and look at where the retention rates as a function of time of the video playing. All right, so here, these new characters come in and there's a huge drop off. This one, it's a black screen, so obviously it just drops off right here. So with this, take the data, all these individual data points, and each frame classified, and dump it into a classifier, learning network, whatever you want, and figure out what is the combinations that drive higher performance. So, so we're working on that already.
So performance of detecting the objects?
No, but so we use a deep learning network to identify the objects. Now we're going to use it again to predict what kind of performance will be, or at least analyze what type of videos lead to higher performance. A very minute level.
In this case, performance is the length of time before someone clicks.
Yeah, right. So a performance, is for example, viewability. Like this is a retention graph. This one does better because most people don't fall off. This one is terrible because it will drop off really quickly. So maybe we look at the Carl Jr. ad and see why is it performing so well. The other example of using this is for user behavior classification. So we have data from all devices, TV, mobile devices, and desktop. For TV, for a subset of TVs with ACR, we can get, for every TV ID, get TV program viewership data. For mobile devices, because we're listening to ads, like ad opportunities, you can see device IDs, the sites, the video content, and segments. Same thing with desktop. And what we're interested in learning is the embedding. Which set of user sites, videos, and segments cluster together? That's one. The other one is looking at TV programs and users. Which users watch which kind of TV programs? So if we find lookalike programs, or look at a new show, a new pilot that's going to happen. Find users that might like it. Right? So the raw data is a vector of video content, so it could be TV program, like a show Walking Dead, and roughly 10 million users, so that forms a vector, a sparse vector of length about 10 million. and it's mostly sparse. So it's the users that saw that program content, right? So vast number of them would be 0, but there would be some users who saw it. And for all our video content, which is about 20,000 titles, we can look at these vectors. Right? And then we train a deep learning network on top of that to learn the embeddings. The question is, how do we visualize something like that? It's great. We learned the embedding, but we're interested in seeing how, having some means of visualizing that data.
Can you explain embedding?
Embedding is, again, a mapping to another space. So, I'll explain embedding with this. So this is, look at this, this is a data set which is in 3D, right? It's got a little gap here, and these are different classes. So in 3D you can visualize it, right? But what happens when you try to visualize it in 2 dimensions? So this is the type of thing that's happening with our data set. In the thing I talked about, that's actually a 10 million dimensional data set, because there's the vectors of length 10 million. So how do you map that into something that we can see? At least for purposes of talk, it has to be a 2-dimensional one, unless we got VR. So there's some techniques out there like isomap, locally linear embedding, that tries to reconstruct this data. But what works really well is this technique called T-distributed stochastic neighbor embedding. So that preserves most of the original data out there once you roll it out. So we try to do the same thing with our programs. So we run TSNE on the Learning Neural Network. This is hard to see, but it roughly maps everything, all the TV programs. Really hard to see here, but there are some outliers here, like Elbow Room over there. Very few people watch that. And Guns and Gear out here, kind of outliers. These are shows that are kind of more popular. How do we know this really works? We zoom into a cluster, right? And once we zoom in, we find a cluster here, and this shows you the relative distance. But these seems to be all the users that like similar type of shows. So, State of NASA, replay of Space Station Live, ISS Expedition, NASA X, mission coverage. And the distance tells you roughly the distance in similarity between the TV programs. So this week at NASA and Space Station Live are kind of current events in the space world, if you will. That's why they're grouped together.
So can I ask, so on that 3-dimensional surface, there's some 3-dimensional distance function, and you want to create a 2-dimensional surface that has a different 2-dimensional distance function that generally maps.
Yeah, what it has to do is, unlike minimum spanning trees, for example, it has to preserve relative distance. So minimum spanning tree can just show you that it's separated. It's computing a tree-based distance, like a KD tree or something. But with this, what TSNE preserves is the relative distances between from the original space, or original distances to a lower dimensional map space.
So the embeddings are produced by deep learning?
Yeah.
So did you use something like word-wave cloud?
Sorry?
Did you use something like word-wave?
Yeah, ultimately, yeah. This is the words. So the words here are the TV programs, and the vectors are the user, like whether they watched it, the sparse vectors.
So these are not documents.
So they're not documents. So for a document, yeah, you look at a word, and then maybe another way of thinking about it is a TV program is actually the document, and the user, actually it doesn't work. So in a word-to-vec setting, you'll have a document, and it shows you the presence or absence of the word in the document, and you enumerate all possible words. So for this, you have a TV program and an enumeration of all users and whether they saw it or not, a sparse vector. So that is the word to vec, if you want to think about it that way.
So you had to try to visualize in 2 dimensions, which you said was hard, but if you could also, let me see if I have this right, you could also find the just distance in the higher dimensional space and just list the distance between any 2 points, right?
But how would you map it, right? So I can have a distance here, and the distance is going to be, like, you need a seed point, and and it gets all warped, like it might all end up together, because in higher dimensional spacing, the distance may be, you end up with, it would only make sense if you want to preserve the distance if you're mapping it in the higher dimensional space, but not when you want to take it in lower dimensional space. So what TSNE does is preserves the distance, but map. So it's kind of like doing a mapping, a projection from there to,
Are you able to visualize for magnitude too? Like I can't imagine all these shows, or is this strictly like topical similarity by distance? Like
this is the question here is, users who watch this show also watch this. So it's like distance is users.
Okay. Yeah, but there's like strength of connections between, like, there's going to be a lot more people who watch Walking Dead and Game of Thrones versus people who watch NASA TV program, whatever else.
Yeah, but this is relative distances, right? So this basically shows you that these 2 users, these are a similar set of users. So the whole point of it is, if you just use like simple distances, you run into the problem where the shows that are highly watched will get collapsed together, right? And you get, that's not the right type of inference to have. It'll just be purely based on the number of users who watch this. The whole point of doing the deep learning and the embedding is to find relative kind of similarity. So you find the set of users that only like watching similar shows.
So did you use word to back, did you use a deep neural network training? And then you fit it into a TSNE to visualize this?
Again, we're not using word to vec. I'm just using that as a similarity, as an analogy.
Yeah,
So
user, yeah, and I understand that, this is kind of like, what user likes to watch, like this similar kind of, show, right? So you use a deep learning to generate this kind of like representation.
yeah, the point of it is, if you're, your original point, if you want to use just simple cosine distance, right, then you'll end up with a high concentration of the most watched shows. And what would get grouped together are all like shows that only one person watched. They'll all get grouped together. And every major show gets clumped together. So the whole point of this is to find, the whole point of learning the embedding is to find shows that are similar. Or similar set of users watching.
So what does like 0, 0 represent the point of 0 on YouTube and 0, 0?
I mean, that was just a point of origin. The numbers, this is all relative distances. The actual numbers.
So what V1 represents?
It's just a mapping, just to visualize it in 2D space. Don't, like this thing actually doesn't matter.
So those numbers have no meaning?
Well, it's just no physical meaning. No. It's just a embedding into the space.
But they indicate relative distance.
Yeah, relative distance. Yeah, so, okay. So, for example, this one, if you look at this, 0, 0.1, so this, you might come up with something like these 2 shows are, a similarity of 0.5, whereas if you take the distance between Space Station Live and ISS Expedition, you might get a distance of 10 and 40, about 20.
How is this different than like some sort of basic sandwich-based clustering like Gauge?
So again, you can run k-means on the deep learning network. So the whole point is that embedding is learning the underlying manifold of distances. So when you do k-means, you have to specify a distance function, right? So the question is, what is the distance function you use? You might use Euclidean distance, which makes no sense for images or something like this. So the first thing to do is learning and embedding a space from which you can calculate distances. So you can imagine once you've learned the embedding in a deep learning network, you can run k-means on top of that to find a cluster together.
Okay. That makes sense. Thank you.
Cool. So, the other thing we do is, rather than looking at similar titles, we look at users that are similar by mapping it to users, titles, sites, and segments.
What program are you doing the graph about? Is that your own or is that Neo4j?
Good question. Nice question. So, what we'll do is, next, Michael and Sonia are going to present more of the tools that we use, which is, Spark, most of our production code is all written in Scala, but for the illustration purposes, we're going to be using Jupyter notebooks with R. So that visualization was with R Shiny on a Jupyter notebook. So for you guys now, we'll talk about some of the tools and a platform that we can use for a hackathon, and it just shows you how easy it is to work with a cluster, a Spark cluster, or work with a deep learning library with just a few lines of code in a Jupyter notebook, where you can easily visualize things. And what Michael will show is an in-house Docker image, a Docker container, where you can deploy a Spark cluster at the push of a button, which is pretty huge.
Just had a quick question. What was it about TensorFlow you were saying that did not make it useful for what you were doing here?
Couple of reasons. So one is TensorFlow is, you can always muck around with the source code, and the source code is in C++, which makes it a little unwieldy, especially because our stack is in Scala. The second is, if you don't want to muck around with the C++ code, it doesn't expose certain things like the features that it has learned. It's kind of meant to be more as a black box. It's good for image classification, if that's your purpose. But if your purpose is to extract features, image features, or NLP features, then TensorFlow doesn't have an API that exposes that.
It's more of a computational framework, like
Yeah.
Hadoop is for MapReduce, but this is like more of low-level computational framework for.
Well, TensorFlow, although it's written in C++, it's not very low level. It's kind of high level in that it doesn't expose a lot of the low level features in its API. Like what is the features that it's actually learning? You can't really extract that.
Kind of like, you basically come up with your graph, right? Come up with
Yeah.
a bag of
Yeah.
operations,
So you can-
and that's what you need to do.
You can feed
Just like
forward, you
computational
can
framework.
train it, you can do all sorts of stuff. But if you want to dive more into detail and look at the representations and the features themselves, then you can use Cafe or Piano.
So everything is open source, but you have to go through the code to extract features.
Parts of it is compiled,
Oh,
so I don't think everything is.
No, it's mostly open source.
Sorry?
It's mostly open source.
Yeah, but some of the things where you take in, one of the issues that I have right now is the protobuf library where you take in, look at the data that comes in, that part is a black box. So a lot of the things, if you want to encode your own features, you can't do it.
The protobuf is open source, right? And the only thing is it was
if you want to spend time like a year,
No,
like,
only thing that was
going
not
into
given was the
protobuf.
basal build of a protobuf in that. Because I worked with TensorFlow internally at Google, and only thing that was not given was the protobuf
Protobuf one.
build, basal build, which you can kind of write.
Sure,
yourself.
if you work at Google, if you know the library very well, by all means compile it and have fun with it, but
Yeah, okay.
So maybe they should actually.
I mean, there are some people who actually wrote those specs for bases and stuff.
Yeah, but that gave me some trouble.
I know you said it had some hidden stuff to it, but did you say you thought that TensorFlow was good for NLP kind of stuff if you're not really?
Yeah, absolutely. It's the simplest way to get started because cafe and piano take a lot of time to get acquainted with it. So.
And also Cafe is kind of like, Facebook is built on Cafe, like the whole Facebook's image recognition.
Now we're going into
okay, like
political discussion. Yeah, I mean, ultimately, if you're really hardcore, then you might go with piano and Haikuda and go all the way there. But TensorFlow is really good at getting started, and it's real. I mean, I will give it that. It's good for starting applications. If you don't care so much about diving in and mucking around with the source code, then and you want to build an image recognition app, you want to build a text extraction app, it's great for that. But you know, if you want to actually look at the features, learn, etc., and you're not from Google, then it's harder.
And mostly it was built for scaling actually.
Yeah.
TensorFlow is just to scale, like if you want to scale your training and your serving, then it's pretty good.
Yeah, that's
Not
partly
just
the reason why it was written in C++, right? Cool, so I'll hand it over to Michael.
Yeah, Michael.
Is that a real image?
Yeah, that's not real station. That is Zion National Park. The subway hike from the bottom up to Archangel Falls, and on. Did you take that yourself? All right. So great. My name's Michael, as Dave mentioned, and I'm a staff machine learning engineer here at GoodMap. And let's see. So wanted to briefly review some of the tools we have and use here for doing data analysis and machine learning. But first, I wanted to ask, as a survey, who here is familiar with Spark? Who uses Spark day to day? Okay. All right. Well, I guess I'll give a little bit of an introduction. Okay. So Spark is a framework for distributed computation, data parallel computation, across a heterogeneous cluster of compute nodes. And the fundamental unit of data in the Spark core RDD, and the RDD is specifically stands for Resilient Distributed Data Set. It's resilient in the sense that it can be reconstructed in the case of the loss of part of its data set or contents. It's distributed in the sense that it can be partitioned and distributed in a data parallel way across multiple worker instances. And it's a data set in that it holds data. It's more like an array, though, a data array. So, in a nutshell, when we're working with RDDs, I rip off this image I just found on Google Images. And this is basically your fundamental Spark program. Again, this is working with the basic Spark core. We read some data in to an RDD, which gets replicated and partitioned across worker nodes. We apply one or more transformations, which have an iterative effect or a chaining effect. This produces a lineage from one RDD to another. And then we perform an action on that RDD, and that returns the result of that action. All of the operations up to this action are by default lazy or deferred, in the sense that what's happening here while you build this computation is Spark is actually building a lineage or a computation or graph of dependencies among data sources, among RDDs and transformations, and an execution graph for getting the final value that you're looking for. Now everybody's a Spark expert, right? So, well, I'm about to blow your mind, because there's more to it than that. As a matter of fact, we've got this other picture I got out of Google Images. Now, we just went through Spark Core. This is where we've now mastered Spark Core. But there's more. So, Spark is bundled with some additional add-on libraries and capabilities. Spark SQL, Spark Streaming, MLlib, GraphX, primarily among them. And in my view, in my day-to-day work, I do a lot with Spark SQL. And Spark SQL is special in that it presents an abstraction for tabular data called data frames. If you've worked with R, Pandas R? It's Python? Yeah. Okay. Perfect R data frames or Pandas data frames. The terminology is intentionally similar because the Spark data frames inherit a very similar interface from its ancestors. One of the main differences, though, the Spark data frame is, under the hood, a data frame is designed to parallelize your operations across the Spark cluster. Now, data frames being the reusable abstraction that they are, again, it's basically a table. They are finding themselves in more and more places in Spark now. They have insinuated themselves between MLlib and this new thing called ML pipelines. Maybe that's why they're the same color, okay? is ML Pipelines builds off of MLlib, and it basically is like what you get when you standardize the process for training, storing, loading, and executing machine learning pipelines and models using data frames and the underlying MLlib algorithms. In addition, there's this newfangled thing called graph frames. I was hoping to demo that, but I don't think we'll have time, which is basically like GraphX and data frames had a baby. And then what we can see down here is we can pull in data from various data sources. Here at VideoAmp, we use HDFS or Hadoop, and Postgres, and JSON, and Cassandra, and another thing here is not listed called Parquet. And then up here, we can see the primary language bindings for working with Spark programs. Scala was the original, followed by Java, and Python, and the latest member of the Spark front-end family is R, or Spark R. And hopefully we'll have the opportunity to see some of that when Sonia presents.
If you could work in SQL and Python and as data frames or our data frames, can you pretty much make the leap to those in Spark?
Yes.
They're that close?
Yeah, I think so. I mean, I have to say that I'm not by any means a Python expert. In fact, I've never used Pandas. But I can say that the data frame fluent language that's present in Spark data frames combined with ordinary SQL is very powerful and very easy to work with. And I am told by my coworker that actually, who is familiar with Python and R data frames, that Spark data frames are practically an invisible layer, an invisible transition. So, now we know everything there is to know about Spark. Any questions about Spark? Okay. Is that no? Okay, great. So another technology I want to show here is something called Project Jupyter. Now, have you guys worked with an interactive notebook environment in your scientific computing or any kind of interactive computing? Like IPython is the predecessor to Jupyter, there's Jupyter. There's Databricks Cloud, Databricks Notebook. There's, and then another big one now is Zeppelin. So these are all tools that provide a so-called notebook web interface that lets you enter Markdown, HTML, and code in a sequence of input cells connected to a kernel which will execute the code in the code cells and then display the output beneath. So this is the Jupyter homepage. Jupyter's roots are in Python. Like I said, it was originally called IPython. This was going to be IPython 4, but they renamed it Jupyter with a Y, so you know it's Python. That being said, it has a very modular system for interacting with a wide variety of back-end systems. Jupyter defines a cross-platform wire-level protocol for a notebook front end to communicate over WebSockets with a kernel on the back end. And that's where you get the ability to connect to any kind of back-end computational system that you want, given the right kernel. Okay, so all that being said, next I want to get into okay. So this is a Spark cluster. It's a Spark 1.6.1 cluster, which I brought up, I don't know if it has the uptime up here. I don't see it, but I brought it up around this time. So that's actually UTC, but it was about 45 minutes ago. And we have a script here, which basically, well, let me go into a little more detail. So we have an in-house process for standing up clusters in, let's say, under 5 minutes. And basically the way it works is we have an internal Jenkins build job for the Spark distribution, building it from source, along with any patches that we have internally. That builds a Spark distribution. We have a Docker file, which we can use to Dockerize that distribution, and we tag it with the appropriate version number, and we push it to our Docker hub. At that point, we can run a script specifying the number and class of worker instances we want, and it will bring up a Spark cluster in under 5 minutes or so. So in this particular case, I asked it for 4 C3 8XL instances, and that's what we got here. But you can ask for whatever instances you want, including G2 instances for GPU accelerated computation. And on a side note, yeah, there is a way to do distributed deep learning through Spark. There are various libraries for doing this. One of them is called SparkNet, and it includes an interface to Caffe, which itself is written in C++, so there's a Java wrapper around that. But the long and short of it is you can take a very large training set and you can apply a divide and conquer approach to learning, training on various slices of your data set and then merging them. But yeah, I'm not going to have time to demo that tonight. So let's say now we have this cluster up. Next, we want to do you have to, I'm gonna say no. And right now we do, but I don't think you have to. That's kind of bleeding edge stuff for us right now, to be perfectly honest. Kind of something I got working over the weekend. But yes, so Spark has the capability to distribute jar files as part of its job configuration that will get automatically put onto executor class paths on the worker nodes. So now I'm going to get into a Jupyter notebook and do a little demo here. So we have this library. It's an in-house library called Jupyter Stone Util. And basically, this provides a simple capability for us to specify startup configurations, which load in various dependencies, and execute certain lines of code. So in this case, we're adding various Spark libraries to our class path. We're adding the Ammonium Spark 161 library. And it's doing a few other things here, running some code, and at the end it's telling us to adjust the Spark config with Spark conf, then access the Spark context in SC, and the SQL context in and SQL context. All right, so here we are, Spark context, and with this ad hoc cluster, which I'm calling Sparky. Let's see, I need to, here we are. So this gives us Sparky's master URL. And I think, actually I already had it in there. Okay, yes, so it's right here. We're going to create an app called similar titles. We're going to take up every core on that cluster. Oops. 128 cores. And it's a tuning parameter, I'm not going to go into that. Execute memory, other things I'm not going to go into. All right, so now we've configured our cluster, and now we can take a look here, and you can see that nothing's running. Okay, that's because we haven't asked it to do anything yet. So the first thing we're going to ask it to do is, so the rest of this exercise I'll state is basically taking some pairs of content, title, and consumer interest edges and computing all pairs similarity between all of those titles using cosine similarity. Okay, so first thing we're doing here is we're getting all of the titles. We're creating a title vector. Well, that's titles. And we're creating a couple of bidirectional maps. So when we convert this into a matrix, matrices are indexed by integers, but in our mind, we want them to be indexed by words or titles like these. So that's why we have these maps, title map and title map 2, which is the inverse. Next up, so we're going to pull in the MLlib linear algebra package, the distributed linear algebra package, and basically what we're doing here is we're creating a data frame consisting of consumers and titles. We're mapping them to a triple consumer, title, and a weight 1.0. I'm going to kind of go through that gobbledygook, but what we end up with is a row-oriented matrix with it's a row-oriented matrix where every row is a consumer vector. So the columns represent the titles and the consumers that intersect where we have a view that expresses it can be considered an expression of interest. So we've got this content consumption matrix. Then Spark, handily enough, comes with this method called column similarities, which lets us express this similarity computation as another matrix. And then we're going to take that similarity matrix and we're going to turn it back into a data frame with columns title 1, title 2, and similarity, and cache it. Now, running this takes about 30 minutes, so I'm not going to execute this final step. But at this point, I'm going to turn things over to my colleague, Sophia, and she's going to show you a little bit of data analysis of these similarity metrics, similarity values. Thank
Hello everybody, my name is Sonia and I'm working here as data scientist. So first let's start, if somebody of you worked as data scientist or have some experience in data analytics or some technology stuff. So I'm going to show you two examples how Michael talked about metrics of the similarity metrics, and we can run analysis on top of it, just to cluster different titles and how similar they are based on their viewership. So in order to do that, I use a graph. So I can filter values, similarity values lowered at some particular threshold, as you can see here, and I can run graph on top of this analysis and find the disconnected or connected components. So these connected components will represent my clusters of similar shows. And below you can see just several examples of these shows. For example, this cluster number 20 shows titles for news, for example. Next cluster shows titles for some horrors or action, or how you name them. And the last cluster is interestingly enough, this analysis does join together Spanish shows. Even though we never employed any language technique or so on and so forth, but it does show, it does cluster different shows based on the just viewership history of customers. Okay, so now I will, that is a similarity matrix. Yeah.
So what's the graph here? What's the node? What's the edge? How do you define the graph
okay.
here?
So let's go back here. The graph itself are values from similarity matrix. So I find that links and my edges are shows which have a high similarity in between them. So edges, vertices of graph are different shows. Links are, and the weights, actually it's cosine similarity between them. So that's how it is. If you have one show and have high affinity to the other show, this show has other high affinity to other show, they do form the cluster. And so these clusters, they fall apart into different disconnected components. You can find them in just recite how they. It works pretty well, so I've been amazed to see that just viewership history can give you so good clustering of shows. That's amazing from my perception. Okay, next example I wanted to show is quite a simple analytical example. Can be we can do on top of all these clusters and platform and so on and so forth. So it's related to viewership analysis. So actually what I did, I took a pretty small sample of viewership history for during 2 weeks in February. So during these 2 weeks of February we had debates, Democratic debates, Republican debates, and I decided to compare this viewership with, for example, Simpsons. What this map shows here, you can choose viewership and look at the distribution of percentage. What is percentage of population of this particular county? Relation here is per county. What is percentage of people viewed this particular show? for example, Simpsons or political debates or democratic debates. So that's the essence of this maps. So I can choose, for example, Simpsons here. We can choose Democrats. TVs takes some time to load this map. Sorry. On the right side, you can see a histogram of percentage inside of this map. You can click into this map, for example, and this distribution will change, so you can analyze just maps which are in the view.
Excuse me. You are getting this information from those bid requests, right? Bid requests.
This particular, no, I cannot get that. This particular information is only for TVs.
It's from the smart TVs.
It's for
Okay.
TVs. It's not for mobile desktops or digital.
So this is coming from set-top boxes.
No, smart TVs.
The Visio one that you showed,
Hmm?
is it from Visio one that you showed in the first slide?
But estimation is like, since Visio and TV they have very good representation, so it's representative data set. We verified this, and you can tell that this percentage of people actually, that's an estimation of percentage of people who view this particular show. So you can So what we can see from this map, for example, there are islands of higher percentage. For example, you can click on this map and to compare different views. Inside of this particular county is Clearwater. And you can see that percentage for Republican TVs is comparable to Democrats. For Simpsons, for example, it's much lower. But in general, what is interesting, the Republicans debate that they had much higher viewability than Democrats debates, approximately 1/3 higher. And the Simpsons are comparable to Democrats. But Simpsons, they are taken, since I had 2 weeks of it, and these are all took into account the entire 2 weeks. So these people who at least once watched Simpsons. So you can imagine what it is the volume of people who view this. Okay, what else we can do here? We can go, for example, on more detailed exploration, and we can choose what I have main here. For mains, for state main, we have different data for Democrats, Republicans, and Simpsons. We can actually sort them and to go, for example, to the county with this particular set of values, and to look at them, what's going on in this county, what's going on in the neighbors county, what is distribution around this map, and so on. So that's actually it.
So is it doing the computations online, or is it all stored that for this state, this
Basically, my
percentage
data,
have viewed,
data
or
which I
you
use
have
here,
users?
data I use here, these are represented in this table. So I just prepared all calculations because there is no need for real-time calculations.
Oh yeah,
So
so I was
just
wondering if it was
calculated.
taking time to load it.
Are you using Tableau to?
No,
So
that
they
is shiny maps in R.
Oh,
Sorry, I
Shiny
forgot
Maps.
to mention what I used here. Sorry, it's shiny maps in R. So, okay, any other questions? No. So basically that's it. Thank you so much for your attention. If somebody
You want to
wants.
So thank you guys. If you have any interest in the hackathon, you've seen the last 2 talks were about a very easily deployable Spark cluster. Like we spun it up in 5 minutes. Cluster with more than 250 gigs of memory and 128 cores. And the second one was visualization tools. So the idea is to kind of think of, like, use different deep learning libraries, come up with interesting analysis of the data. We can look at some of the data that we have and just try and visualize and use the tools that we have, our Shiny and Jupyter notebooks, which makes these things really simple. So if you have any interest, talk to one of the organizers, me, Elnaz, or Kevin. Cool, and you guys.
What's happening, buddy? I get to talk to you. Wrong hand, I gave you the wrong hand. So last time we talked, you had split out of your job. Have you ever moved?
Nice data. This is a big issue.
Then it was a race to sort of build more and more complicated networks for more and more complicated tasks. So the key breakthrough was in 2006 with Jeffrey Hinton again and Ruslan Salakutnikov, where they trained a very large restricted Boltzmann machine, convolutional neural net on large data set. That really, this algorithm to do that really opened the floodgates to more and more complicated and deeper neural nets that came to be called deep nets or deep learning. This paper kind of coined it. And then it got more and more popular as industry took off. So Demis Hassabis started the company DeepMind, which got acquired by Google. Then Jan LeCun went to Facebook. Jürgen Schmidhuber, who worked in recurrent neural nets, a number of startups. Li Deng went to Microsoft. Ilya Sutskever, who was a student of Hinton, started a company called OpenAI, which was partially funded by Elon Musk to explore beneficial applications of deep learning and AI. And I think this whole field became very mainstream and popular once these type of books started coming up, like Deep Learning for Business Leaders. So, just my personal background, I worked with Jeff Hinton. So this history is, by the way, very biased because of my background too. I worked with Jeff Hinton and his group in Toronto, then worked with Demis Hassabis, and also at the Computational and Neural Systems group at Caltech. And I've been utilizing deep learning in my past two startups. So the question is, what is deep learning really good for? I mean, you can obviously massage it and torture it to work in a number of settings. But where it really shines is for natural scene statistics. So when you have images, speech, or when there is a lot of latency. But this is passed through a nonlinear function. So here it's sigmoid. So what that allows you to do is, in this example, use it for classification, but encode more nonlinear functions with it. So take linear regression, pass it through a nonlinear function to get much more interesting functions out of that. Why it got a lot of interest in the neuroscience community is Rosenblatt thought of this as perceptrons could model neural synapses. So in the brain, what you'd have is, how many of you are familiar with a picture of a dendrite? So in a typical dendrite, you have a cell body, an axon, and a lot of inputs coming to that. So one way of thinking about it, why perceptrons were very interesting for neuroscientists, were all the inputs coming in were from different cells. And there was a cell body inside, and it fired once it reached a certain activation energy. And then you got an output through the axon. That became an interesting model for a very simplistic model of the brain. John Hopfield at Caltech took it a step further, and where now all of these inputs could come in to a densely connected matrix, and that was actually a pretty realistic model for memory in the human brain. So that got a lot of interest among computational neuroscientists. So that was fine, but the question was, once you start fitting a nonlinear function like this, fitting this is very difficult. With regression, there's a very simple closed form solution and you get these weights out, super simple. But how do you handle something like this nonlinearity, right? Especially now that you're dealing with a multi-layered neural network. So these perceptrons feed into other perceptrons, which feed into other perceptrons. So training all of that together and finding the weights for these things are very difficult. So the work stalled for a while until, then I'll talk about a couple of applications in Adtech. Can't really go too much into the implementation details there because these are our products and future products. And then at the end, there was some interest here about having a hackathon, some sort of visualization and deep learning hackathon. So how many of you might be interested in that? Okay. So ideally we'd do that on a Saturday. We can provide the space and also some of the resources, the cluster and everything to run it. And for that, Michael Ullman at the back in orange, and then Sophia. After I go through my talk, they can talk a little bit more in technical detail about some of the tools that we use, including Spark and Jupyter and SparkNet that you might find useful in the hackathon. So we can help you run, spin up some clusters, run whatever you need. So, going a bit into the history of deep learning, why did it all come about? So, it all starts with, a data set that you can fit with linear regression, right? Straightforward, simple. Don't even try deep learning. When your data gets more complicated, something on the right-hand side, that's when you need something more complicated, like a quadratic function, for example, right? So when data is more nonlinear, it can be fit just by linear regression or simple regression alone. That's where deep learning starts becoming handy, because you can encode nonlinear functions. So the first step of this came about with Marvin Minsky coined the term perceptrons. So what perceptrons do is they encode a kind of linear regression part here. So each of these x0, x1, x2, xn, there are different dimensions of the data set and a weight assigned to each of them, and there's a simple sum. So this is the linear regression.
I'm Elna. I'm one of the organizers. Kevin and Deb are also organizers for this meetup. And we're very happy that you guys came here today. The folks at Video App are going to tell us about the work that they're doing. I also wanted to let you know that we have another exciting meetup on Friday at 3 p.m. at USC's Information Science Institute, and you should check that out. I also I wanted to note that even though you guys did register with Video App, but we also have a sign-up sheet for each of our meetups. So I did share the link to our sign-up sheet for tonight on the Facebook page and the Meetup page, and I would appreciate if you guys go in and enter your information. So if you're looking for collaborators, you want to network, or you want to get hired, or you want to recruit talent, and just get to know people, I think it's best that you guys go on that sign-up sheet and add your name. We have one for the last meetup, and we're going to just be adding the names to our database. So this is Deb. He's one of my dear friends, and he's very good at what he does, and he's going to tell you about his work at Video.
Thank you. Thank you guys for coming. wondering what on earth deep learning is? Just to get a go ahead. Yeah? So everyone else is an expert?
Space in between.
So how many are experts in deep learning? Okay. All right. Well, you guys might be a little disappointed if you're an expert here, because I'll try to cater this more towards a background in deep learning, what it's all about. Have a little demo or a do-it-yourself exercise. So hopefully at the end of this, you can go home and try it out. So Jack over here, he runs our company blog, so he will have a write-up about this, so you can go home, test it out, play with it yourself. And Jeff Hinton and Rumenhart came up with the backpropagation algorithm. So what the backpropagation algorithm does is, so you have a large training set, and you have some multi-layered neural network with input layers, hidden layers, output layers. It goes through a forward phase where the training data is passed through, and it identifies some label there. And it does a backward step as well, where each layer tries to recreate the layer before it. So it's training on its own. So a version of this is a recurrent neural network, which is used for unsupervised learning, where the output layer just has connections to itself and to other layers below it. So there's a process where you pass the data forward and you see what you get, then run it backward and get an error out of it. And the goal is to minimize this error over multiple iterative steps. So another advantage of neural network, especially a multi-layered neural network or deep network, is that it's a generative model as well. So you can run it in forward motion and generate things out of the network. Try to figure out what the network has learned. So there was an interesting article by Jeff Hinton in Science magazine in 1995, where he conjectured that this is another way of, people were thinking about the brain as a neural network. So the conjecture was that this is, going forward is the waking phase that we all have, and it passes through and our synapses get trained. And the dreaming state is when the neural network starts generating on its own and to calibrate against what's going on. So that was a postulate of why we wake, why we sleep, and why we require sleep to train our brains. And most animals that have complicated brains actually dream. So after backpropagation came into being,